Then let's turn to the next page. I think this was also homework, page 33. So we've got a heating curve below of liquid water being heated on a hot plate. So that means we already know it's beginning as a liquid. And you could figure out already, if this is liquid, here where it flatlines, that's where it's uh, vaporizing, it's boiling. So that's going to be liquid and gas. And then this is going to be gas over here. Okay, label heating curve with phases of matter. Oh, just did that. What's the boiling point of water according to the heating curve? So the boiling point is the temperature when it's boiling. So here's it's boiling. If we continue this over, we see that that's 100 degrees Celsius. So it stays 100 degrees Celsius the whole time it's boiling. During which interval is the phase change occurring? It's occurring when the flat section, here it's boiling, so RS, R to S. During which interval is average kinetic energy rising, increasing? So average kinetic energy is, remember, related to temperature. Average kinetic energy is related to temperature. So when is the temperature rising? It's rising between Q and R and S and T. So this guy and this guy. Which interval is potential energy increasing? Potential energy is increasing here at the phase change. That's because the energy that we're adding, it's not changing the temperature, so the kinetic energy is not changing. Instead, the potential energy is changing. So that's RS. Let's see here. We've got Doug Pond. The temperature of the ice on Doug Pond is negative 6 degrees Celsius. Ice will begin to melt at 0 degrees. What must happen to the molecules in the ice to get to 0 degrees Celsius? So we need a temperature change. And we remember that temperature goes with average kinetic energy. So, and we need to gain it because we need to raise the temperature. So we need to gain kinetic energy. So that's A. Once the pond reaches 0 degrees Celsius, does the ice on the pond need to gain or lose energy to turn into water? So at 0 degrees Celsius, we're already at the melting point. In order to go from ice into water, solid to liquid, we need to add energy. We need to gain energy. And what type of energy does the pond gain as it transitions from ice to water at 0 degrees Celsius? Well, it's staying at constant temperature, and it's doing a phase change. Phase change. So that means we're talking about potential energy. If it's going from ice to water, it's going to have to gain potential energy. So let's see here. Another way of saying that, so technically it is gaining mechanical energy also. But we're going to say that ice molecules gain potential energy to break the bonds in the ice. Okay, let's continue. Page 34, we skipped. You don't have to do anything with page 34. On to page 35. Page 35. 610, heat transfer activity. This activity contains a variety of situations, etc., that during the specific heat of a metal lab, a student places a hot piece of copper, into room temperature water. The copper started with a higher temperature than the water. In which direction did heat flow between the objects? So remember, it always goes from higher temperature to lower temperature. Oops. The higher temperature in this case was the copper. So it's going from the copper to the water. What happened to the temperature of the copper during the heat transfer? Well, as it gives heat away, the temperature is going to decrease. It's giving heat away, it's cooling down, it's not changing phases or anything, it's just cooling down, so the temperature is decreasing. What happened to the kinetic energy of the copper during the heat transfer? Well, if the temperature is decreasing, the kinetic energy and the temperature, they're proportional to each other, so it's also decreasing. Was there a phase change? No, when you guys did this and you put the metal in the water, the metal didn't melt or freeze or anything. And if it's already solid and it's losing energy to the water, it's not going to change into a liquid or a gas, because in order to change to a liquid or a gas, it needs to gain energy. So there's no phase change for the copper. How did the potential energy of the copper metal change during the heat transfer? Since there's no phase change, let's see if I can write that. No phase change means no change in potential. So the potential energies remain the same. Now, what happened to the temperature of the water during the heat transfer? So the heat's being transferred to the water. The temperature is increasing. It's gaining that energy as kinetic energy. So, which is temperature also. So what happened to the kinetic energy of the water? As the temperature increases, the kinetic energy is also increasing. They're both increasing at the same time. Was there a phase change for the water? Don't think so. We didn't see any like gas or any steam coming out. So that's possible with a really hot piece of copper if you were to put that in water, but for like a fairly hot piece, you wouldn't see a phase change. So there's no phase change. If there's no phase change, there's no change in potential energy. So that remains the same. And the copper was in direct contact with the water. What type of heat transfer occurred? So that's called conduction. Conduction is when you're in contact with each other. So what I want you guys to do now is turn to the next page. We've got a similar scenario, page 36. Here we have got ice cubes already at 0 degrees Celsius, and they're added to room temperature water and begin to melt. So I want you guys to answer these questions, figure out, is there a phase change? Is the temperature changing? That sort of thing. Then there's another one about, well, let's see, what do we have? All right, how about, I'll do number 2, and then you guys will do number 3 and 4. So again, we've got ice already at 0 degrees Celsius. That's the melting point, temperature which water melts or freezes. And it says it's beginning to melt in the water. The water started with a higher temperature than the ice. In which direction did heat flow between the objects? From the higher temperature to the lower temperature. The higher temperature was the water. So water to ice. What happened to the temperature of the ice during the heat transfer? So this is a little tricky. The temperature of the water is higher, so it's giving energy to the ice, but the ice is melting. It's undergoing a phase change, which means the ice is not actually changing temperature yet. It's remaining the same because it's doing the phase change. It's melting. During a phase change, temperature stays the same. What happened to the kinetic energy of the ice during the heat transfer? Well, if the temperature is the same, kinetic energy is the same. Was there a phase change for the ice? Yep, it's melting. It's going from solid to liquid. How did the potential energy of the ice change during the heat transfer? So as we melt, as we go from solid to liquid, we're adding energy to it, and the energy that we're adding is potential energy. So we're increasing the potential energy. What happened to the temperature of the water during the heat transfer? So the ice is undergoing a phase change. The water is not undergoing a phase change. So the water itself is not doing a phase change. It's still liquid, which means if we're taking heat out of the water and it's not changing phase, the temperature is what's changing. So the temperature is decreasing. All right, that's like when I'm sure you've had water and you put ice in it and the water gets colder. That's the point of putting the ice in there. What happened to the kinetic energy of the water? The temperature decreases, kinetic energy is decreasing as well. Was there a phase change for the water? Nope, the water doesn't change into a solid, it doesn't change into ice. How did the potential energy of the water change during the heat transfer? If there's no phase change, there's no change in potential energy. And the ice is in direct contact with the water, so again, that's conduction. Alright, so you guys are going to turn to pages 37 and 38, and you're going to do those. 37 is about a cold glass of water and water vapor is condensing. You can see it in this photo here. And then 4 is about water being on a branch and the water turns into ice as it hits the tree branch.